So continuing, I just described the position as a function of time. Yes, so I'm going to move on and describe the next special word or concept called the velocity. And the velocity is definitely related to the speed, but it is not actually the same thing as the speed. I'll show you why in just a second. But the velocity comes with a mathematical function symbol, little v of t, like this. So, all right. So I'm just going to, what I'm going to do for the purposes of this video, because this video is about definitions and relationships that are calculus based, I'm going to go straight into defining the relationship between position and velocity with calculus. So the idea is the velocity as a function of time is the time derivative d by dt of the position function x of t, where the position function is up here. So it gives you a lot of information to look at the following way of defining the velocity. So I'm going to leave a space, and you'll see why in just a second. But let's think about what is velocity meant to describe to us. So velocity, if you think about it, it describes something about how an object translates or changes position, but also it's got something to do with how much time did it take to have that translation or displacement. So the way I'm going to define the velocity is actually very natural. It's based on just how we think about the language or the meanings of the words just in the language. So it really is, what is the displacement of the particle, that is how far did it travel, divided by how much time did it take to do that traveling. But this velocity that I want to describe right now, that's based on calculus, actually is what's referred to as instantaneous velocity. And this instantaneous velocity takes into account small moments in time during which the object's position can displace. So in the spirit of those small moments in time, I'm going to imagine taking the limit as the time duration becomes that calculus limit, or it really turns into a small moment in time. And the upper thing is, so this displacement here, this displacement is written right here. But T2 is related to T1 in the sense that T2 is that moment in time later than T1. So this is how much time we have to wait to get between the time T1 and the instant of time T2. So the limit that delta t goes to 0 is going to put a little dt here, but it's more interesting in the position. So this displacement that I'm going to put up here is going to look like this. It's going to be the position at the later time minus the position at the earlier time divided by this delta t, which I'm going to go and ask that delta t head towards 0 but not actually become 0. That's what calculus means. Go and do this such that you're still always above 0 but not equal to 0. So yeah, so it truly is the difference in position between some earlier time and some later time divided by how much time are you looking at. But then you go and you look at the instantaneous, that is, you take the limit that time duration becomes a moment, an infinitesimal moment of time. All right, so same spirit, I'm going to describe the definition or the relationship for the acceleration. So the acceleration is given the symbol a of t, like this, and a of t simply is related to v of t this way. So the acceleration function is simply just the time derivative of the velocity function, and the velocity function is the time derivative of the position function. So quickly I can say that this is d by dt of d by dt of x of t, which is the same thing as d squared by dt squared. It's the double time derivative of the position function. Yeah, this is just sort of basic calculus relationships. But analogous to the situation where the velocity is the time rate of change of the position can be written with this difference divided by a time duration in a limit. It's the same idea. We can take the limit as the time duration heads to 0, or the moment becomes infinitesimally long, and we're looking at the difference between the velocity at a later time and the velocity at the earlier time. So we're looking at how the velocity has changed, but we also want to keep track of some aspect of how long did that change take, and that's what acceleration is about. Acceleration is how fast, how fast did the velocity change. That is what acceleration answers, and this is mathematically how you ask how and how fast did the velocity change. Yeah, so there's a really important thing I need to go and clean up in order to finish this introduction to the calculus relationships, or at least the time derivative relationships between these very particular quantities, or the functions, x of t, v of t, and a of t. And that is the units. I think the units are extremely important. So earlier we said that the time is being measured against the unit of the second for the SI unit. The position, we're going to use the meter as the SI unit to describe locations or positions. And I can have positive amounts of meters, but also negative amounts of meters. I can have no meters at all. Yeah, so m for the meter. And so what's interesting is if you go and you look at instantaneous velocity and positions are in meters and times are in seconds, you can see that what's going to happen if you put displacements in meters and time durations in seconds, this is just going to be the meter per second. If you go and you look at the acceleration though is interesting. If you go and you look here in this expression, we're going to have the difference between two velocities. So it's going to be some number of meters per second minus some other number of meters per second, and that meters per second on the top is going to be divided by another second. So this is going to look like meters per second, like this. But meters per second, that's the same thing as meters per second squared. And the reason is because this is 1 over the second times the meter per second. If you think about it, that's just how the fractions work out. All right, so next video I'm going to show you some examples.